Was this a question? Yes. I want to tell you.
They're
Were there, was there heated discussion still? Oh, I was just, I had to climb over to get.
Yeah. Yeah, I mean, it's too funny.
Oh my gosh.
Is there like lights or something?
I was right at the back, so I didn't mind it. How would you
Okay, we're gonna get started now. We're going to find these things quickly. All right, today's first afternoon session is on binaries for the AGB. And our first talk is by Mark Siebert.
All right, thanks. Thank you everybody for being here and for coming in from the very interesting discussion that was just going on. Just to introduce myself, my name is Mark. I'm a postdoc at Chalmers. I do actually most of my work right now on supergiants, but I'm going to talk today about a source that has been one of my favorites of the past few years and is also very, very relevant to a lot of the discussion that just happened. So this is V510 and I'm going to talk about some recent exciting data that we got with ALMA on it and what it can tell us not only about this story of post-AGV mass loss, but also this story of chemical anomalies that we tend to see in these objects. So to get us started, I don't feel like I need to introduce the post-AGB or the post-RGB because of the discussion that was just had, but it is, of course, this very rapid transitory phase where we see all these amazing morphologies start popping up that then lead to the different planetary nebula that we see. And we know that binaries play a very central role in this evolution. And of course, we have a subset of these post-AGBs and post-RGBs that are these extreme protoplanetary nebula that have molecular outflows with really, really large momenta and velocities over 100 kilometers per second up to 200 or 300 kilometers per second. We have a handful of these. We have H2O101, 584, Blue-Ring Nebula, and a few others that we can look at this really exotic physics where we really think that these dramatic mass loss events are actually happening. Now, one thing I want to mention about the post-AGB is that it's not only a site of rapid physical change, but it's a site of rapid chemical change as well, where on the AGB, you only need to worry about chemistry in your stellar atmosphere and then kinetics from the interstellar radiation field. When we move to the post-AGB, you have all kinds of extra factors, including your central star, which is heating up, and ionizing or photodissociating from the inside out. And then you have these very fast winds and shocks that are propagating through your outflow. And then you can also have disks forming as well, where you can actually store molecular material for a long time. And if you look at abundances of molecules in post-AGBs, you get different results from the AGB because of these many different factors. And one of these anomalies that can happen are these examples of mixed chemistry. And this is often seen in dust features, like with PAH detections in oxygen-rich binaries, as well as fullerenes and the silicate carbon stars. And then in the molecular gas, we have like OH231, where you see molecules that are traditionally associated with carbon-rich winds found in these oxygen-rich environments. And I think you could even add a couple more bullet points from some of the results that were shared yesterday with post-RGB sources as well. So this tends to pop up as these sources start evolving. And this is where our source V510 comes in. So V510 is one of these extreme post-AGB stars. It's about F5 central star. We think the distance is about 3 kiloparsecs. And it's an OH maser source. And in 2015, Sahai and Patel observed this with the SMA, where they got these line profiles down here, showing this really, really extreme ejection up to velocities of 150, 200 kilometers per second. And it's losing a ton of mass in the process with this very large outflow. What's more, this is, as was noted in the last session, this is one of the only sources where the binary is actually detected in one of these extreme environments, where Manick et al. Monitored both the radial velocity as well as the H alpha line profile and found a period of about 7 years in a main sequence companion with a mass of about 0.6 on a somewhat eccentric orbit. And what they found was that this H alpha line profile actually modulates with the orbital phase. And when the companion is passing between us and the primary, you see it spread out in velocity. So this is telling us that this companion is actively throwing off mass in terms of in the form of this jet, and this interaction is actually going on as we see it. But most important to this talk is that not only is this an OH maser source, but it has detections of C2 and CN in the optical at the same velocity, which flags it as one of these sources of very odd chemistry. And for a while, this is all we had. It was just this peculiar chemistry source until it was actually covered in a filler program by the ACA. So this is a 7-meter array with ALMA, where it's just spectra in the millimeter, but they get very, very good sensitivity, improving the signal to noise of these CO lines by quite a bit. But it also covers all of bands 3 and 6. So you get tons of transitions from molecular species. And we did an analysis of this line survey and found that the molecules we typically associate with carbon-rich winds and the molecules we typically associate with oxygen-rich winds are completely separated in their velocity space, where the SO and SO2 lines show up in a very narrow component near the stellar velocity, whereas the HC3N, CS, CN, HCN, these tend to show 2 peaks at about plus minus 50 kilometers per second. And so this was evidence that this chemical dichotomy is actually separated kinematically as well, and it is tied directly to the dynamics of the source. Now, this is a great result, but of course, we don't know what these velocity components represent and what that could actually tell us about the evolution and the chemical evolution of this source. So what we did next was follow it up with ALMA. And so I want to be sharing some of the first results that we got out of this ALMA project that I led, where we resolved the nebula and targeted a bunch of these lines to actually place where they're showing up in the outflow. So this is our CO map compared with the HST image, and we see that we have a nice sampling of at least the large scale structures in this outflow. And of course, because this is ALMA data, we can step through the cube and see where all these different velocity components are showing up in the wind. And this is going to be very critical to our chemical analysis, of course. And we detect 16 transitions from 9 different species, including our main outflow tracers like CO and SiO, and then what we flag as carbon-rich or carbon-bearing molecules like HC3N, CN. We have a very low signal to noise detection of methyl cyanide as well. And then we also cover many lines of SO and SO2. And I want to step through and show you just where these things tend to be showing up. So starting with SiO, I'm showing a moment 8 map here of the nebula. And we see this beautiful bipolar shape as well as tons of structure here. The moment 8 maps are nice at getting you the dominant physical structures in any given line of sight. And we have the bipolar structure as well as this high velocity tail here to the southeast. And if we compare this with a moment 1 map, we see that velocity scaling along the nebular axis that one would expect from some somewhat radial velocity scaling. And we see that this tail is our extreme velocity spot that's moving about a line of sight velocity of about 150 kilometers per second. So quite fast. Now, if we step to our 13th CO and our first chemistry tracer, SO, and look at those maps instead, we see that this very bright central component pops up, and notice that the scales have changed here. And if we compare it to the spectrum, we see that that's that very bright central component that I flagged earlier. And with 13th CO, you see a little bit of the extended nebula as well. And then SO, of course, shows up in the same place. But if we look at the moment one map here, we see that its velocity dispersion is actually in the opposite direction to the nebula in general, which is just telling you that this is an expanding disk around at the center of your bipolar outflow. And this is what we expected that this component was, but it's exciting to see. And we also don't detect any traces of rotation in these lines at these spatial resolutions. But now if we move to our carbon-rich kind of tracers, we have CS and HC3N here, and we see a very different story in terms of their distribution on the sky. We see that it's kind of bipolar in shape, but it's going the wrong way. It's going up and down. I'm going to make this picture even worse, because if we zoom in on this moment one map, we see that there's actually substructure in this north-south elongation, where you have a lower velocity component somewhat to the west up here, and it kind of goes this way. And then you have a higher velocity component that's more north-south oriented. So there's actually substructure in the component that this HC3N is going from. And in order to piece together what is actually going on here, we'll move to PV diagrams. So this is the 12CO PV diagram taken along the nebular axis. And I'm comparing it here with HD 101584 because this is the closest analog that we have. And we see a lot of very similar structures appearing. We see this primary kind of hourglass shaped bipolar outflow, as well as this kind of inclined emission from SO denoting your disk. And then we of course have the very high velocity stream that I mentioned before. But what we also see very clearly in V510 PUP is this secondary outflow that we see very completely in HD 101584. There's hints of it, but it's not a complete sort of structure. But here in V510 PUP, we see it all the way out to the lobe, to the tips. And now if I move to some of our other PV diagrams, we see that SIO traces the walls of this hourglass structure really well as the tips of that secondary outflow. The tip of the blue shifted outflow is actually coincident with the OH maser emission. And now if I put one of our carbon-rich species on, we see those two velocity components pop up again, but we now see exactly what they're tracing. One is tracing the tip of that secondary outflow, whereas the other is tracing the very nearby wall of the primary. And this is seen on both sides. So we can do some basic geometrical modeling to try to get a 3D picture of what's going on here, where we just assume a Hubble velocity scaling. And because these are somewhat 3D ellipsoids, we can get a sense of the inclination as well as the kinematical ages of these various components. And it's difficult because our secondary outflow actually overlaps a little bit on this edge with the primary. So it's difficult to get a really good fit to these. But we can do our best, and we get that for the primary, it's inclined about 50 degrees. And we get a kinematic age of about 200 years, which is in agreement with previous characterizations of this from the SMA. And then if we fit the secondary outflow here, it's really well fit by a very inclined outflow. So we're looking basically down the barrel of this bipolar thing. And when you do that, you get a kinematic age that's slightly older than the primary. And now, if I put these two ellipsoid shapes in 3D space as to what's actually going on here, this is what we see in the sky. And then the theoretical inclined view would look something like this, where we're basically looking down this large but very inclined carbon-rich flow. And now if I put back up the PV diagrams from our carbon-rich tracers like HC3N, and remind you where this emission is showing up, where it was kind of in the tip here and the nearby velocity component there. If I just map these velocities onto this 3D structure, you get something that looks like this. And what this is telling us is that these C-rich products are radiating at the tips of the secondary and the nearby wall of the primary. So it's not as simple as this just being a separate carbon-rich flow. It clearly has interacted with this potentially younger and faster primary outflow. So I will leave you with my conclusions. So ALMA, of course, has great capabilities in terms of actually determining where these molecules are showing up, and we see a lot of structures that are reminiscent of HD 101584, including this oxygen-rich expanding disk in the center. And it turns out that the carbon-rich medium velocity component represents an entirely different ejection. But it's not as simple as that, where it's a different ejection, but it has actually interacted with the primary. And I think this is direct evidence that you can actually have this carbon-rich material leaving an imprint on your future evolution and chemical evolution of your source. So I'll leave it at that and take any questions.
Hi, Mark. Mine's Paul. I was wondering, is there a spectroscopic estimate of the carbon to oxygen ratio of the central star?
Not that I know of. I believe it was just carbon rich. It was assigned as carbon rich from the C2 optical bands, but not that I know of. Or do you have? Did you?
Other questions?
Hi, thanks for a very nice talk. This is about the chemistry.
Yeah.
Do you think you can reproduce your abundance for carbon, typical carbon
Mhm.
species, if you have shock chemistry on oxygen-rich environment?
Right.
Because you know, having these carbon bearing molecules is hard to find in an oxygen environment, because you can do it, but finding OH measures in a carbon-rich
Yeah.
environment is going to be even harder.
Right.
So it could be that you have two chemistry, totally different chemistry in the 12 flows, which is
Yeah.
another puzzle. But if you can explain this with shock chemistry or whatever,
Yeah.
you may end up with a single chemistry, let's say, and
Yeah.
two different chemical regimes. That's will be the key question.
Yeah. So it's possible. I am doubtful that one could reproduce it, because this is a very, very different suite of molecules than some of the other traces of this potentially shock or PDR like chemistry. Whereas if you look at something like HT 101584, you see methanol, you see formaldehyde, and then the same goes for the OH sources as well. You see the HNCO, you see a very different suite of molecules, whereas here it's HC3N, it's methyl cyanide. These are like very, very strongly associated with a purely hydrocarbon related chemistry. Yeah, if I saw something else containing oxygen, I would maybe think so, but there's a lot more to be done to see for sure.
Well, thank you for these fascinating results, which is sort of hard for us poor modelers, because to begin with, what's first is second, or what's second is first.
Yeah.
But, we're looking at your geometrical model. You can geometrically just superpose whatever you jolly well please, but dynamically you cannot.
Right.
So what you simply expect, that if your geometrical model is correct, you would expect a hydrodynamic interaction between the two somewhere.
Mhm.
Is there anything in your data that clarifies that?
That clarifies.
Well, whether there would be an interaction between these two figure eight type things.
Other than the association of where the molecules show up there, and it's also where the OH masers appear as well. that's all the observational.
But from your geometry, you can tell where the intersection is, so it could look,
Yes, yeah,
but you haven't found anything.
no, no.
Sorry, thank you.
I think we actually have to hold the rest of the questions, but we can ask more during discussion. Okay, let's thank the board again. All right, next up is Thaisa Danilovich from Monash, and she's going to talk about dynamical chemical shaping of revolved serpents.
Hey, hello everyone. I'm going to talk about two particular stars that show some interesting chemistry from binary interactions. We've all seen, some of these kind of ALMA images where we look at a star, sufficiently high resolution on the AGB. There are some interesting shapes that don't necessarily make sense if we're thinking of single stars. So these images here are of CO, but I want to focus on less standard molecules, and that's going to be SiN in W Aquilae. So SiN, silicon nitrogen, is not actually commonly observed. When I wrote this paper, it had been detected in CW Leo, like most things. And since then, I think Bramwell found it in II loop, and I think that's all. So it's not a very common molecule, and the CW Leo was not very well resolved. So this is sort of the first time we can study it in detail. So the reason this drew my attention, aside from it being a weird molecule, and I like weird molecules, is that we have this kind of weird triangle shape. Right, so W Aquilae is an S-type AGB star, has a known companion. So here the red dot is the AGB star, the yellow one is the companion, which we know is a main sequence star. The separation on the sky is about 0.5 arc seconds, and we know the physical separation is about 200 AU, right? So it's not super close. And we have this weird triangle of SiN on the other side from where the companion is. When we study this further, we also see an arc in the PV diagram where the AGB star is the red thing, and we don't know the velocity of the companion easily, but it's roughly where that yellow dashed line is. So we get this arc. And in this particular case, like the way this system is oriented, what we end up actually seeing in the PV diagram is the PV diagram is looking along the dashed line there. And essentially, we have this arc, which in the moment zero map, we see as a wedge. So it's weird emission, it's over there. Why is that happening? Turns out SiN is formed through UV photochemistry. Our closest source of UV is on the other side of where the SiN is. So by studying the system and, crying about it a little bit, we can work out that this has to be actually a very highly eccentric orbit. So basically the SiN was formed during the periastron passage of these two stars. When the F9 companion was in the dense inner wind of the AGB, it photodissociated, photoionized a bunch of stuff, which formed SiN and a few other molecules. So this is backed up by evidence from SiC and NS, which we also see in this star, and which also require UV photochemistry to form. SiN is sort of the nicest high signal to noise of our observations. So for this system, the W Aquilae system, the orbit is 1,100 years, and the eccentricity that we found was 0.93. So it's highly eccentric. So right now, the companion is not doing much, but at periastron it was. So here's a nice little schematic of it, this time looking down on the orbital plane where the observer is off to the left. Basically, the system is seen almost edge-on, or as edge-on as we can tell. But as the companion gets close to the AGB star, it's in the dense inner region, goes through, leaves a path of photodestruction, which forms these molecules that then continue expanding out with the wind, as they do in general, Meanwhile, the companion has moved on to a less dense part of the circumstellar envelope, where this chemistry is just not happening as rapidly. Essentially, chemistry scales with density. So when it's less dense, less stuff is happening. So we know quite well where the companion is. We also know it's barely moved in 15 or so years. We also have a Hubble observation, but here in Sphere and over there in the ALMA continuum. So molecules are what I normally work on, but my latest paper is about dust, so that's what the rest of my talk is going to be. So in the ALMA continuum, this is band 6, the W Equulae, we found a peak where the AGB star is, the red cross, and unexpectedly, a 5 sigma detection of, well, dust must be where the companion is. Right? The companion is an F9 main sequence star. We shouldn't see it in ALMA. This has to be dust. If we subtract the contribution from the AGB star, also reduce the resolution a little, we can see it even more clearly. There's this little tail of dust behind it. So what's going on there and why? I will explain by the end of my talk. But first, Pi Group is another star that we observed with ALMA. Both of these are part of the Atomium large program. One of the exciting early results from Atomium was that we detected this close-in companion to Pi 1 Group, which had been theorized for quite a while, and now we could see it with ALMA. Right? It's in fact just resolved. It's a happy coincidence that this happened to be like its position in the sky when we observed it and all that. This is our nicest, highest resolution observations. So this is with the extended ALMA configuration, but we also took lower resolution observations. When we make a combined map at a slightly lower resolution, we don't resolve the companion anymore, but we do resolve this sort of spirally pattern of dust behind it. And what's nice there is that agrees really well with the dust tail detected with the sphere scattered light by Miguel Montajes. And in fact, I can superimpose them. We're looking at the same dust, right? In different ways, but we're looking at the same dust. So this is another star with the tail of dust behind a companion. The other interesting thing that we found for Pi 1 Group is that it has a long secondary period of about 15 years. So it's a slightly inclined system, and as we have the companion with its dusty tail passing in front of the AGB star, we have some dips in the light curve. With this period, it's about 15 years. We can also see the tail moving in Sphere. So this is also by Miguel Montajes, related to, so this is our Atomium epoch. Those two images were observed within a week of each other, so they're really contemporaneous. So that's definitely where the companion is at that time. And then we have an additional ALMA image, which my font on that cross went a bit funny, sorry, but it should be in the middle of that dot. And we can see that there's orbital motion and we see the dust changing with time. So essentially, what I have concluded is that we have dust forming in the wake of the companion, right? And this might be a little controversial, but bear with me here. So when the companion moves through the circumstellar envelope, kind of anywhere you want to put it that's at least a little bit relevant, the motion is going to be supersonic. In the inner wind, the sound speed is about 3 kilometers per second, which is the highest it gets, right? After that, density is lower, so the sound speed is a lot lower. Therefore, any companion is moving supersonically. What do we get when there's supersonic motion? We get shocks, right? In other contexts, people have found that dust forms in the wake of shocks, and we ran some hydrodynamical simulations to see how/where the dust might form around these binary systems, and we found, some interesting results. So this is not any particular system. This is for a separation of 5AU, modeled with the hydrodynamic code Phantom. On the left is a density slice through the envelope where you see a spiral from the orbital motion, essentially. On the right, this is some measure of dust nucleation rate. So this is assuming a simple dust formulation where there's a basic chemical network and dust starts to form when temperature and density are appropriate. So you can see here, there's dust forming in sort of these overdensities that we get from the companion motion, and it continues to form further out. In these simulations, we don't have pulsation enhanced dust formation, right? That physics isn't there. The dust formation only comes from the other shocks in the simulation. This is separation of 5 AU. So what this can tell us is that if we have a close companion to an AGB star, we would get more dust formation than we would expect just from the pulsation enhanced dust formation. At a separation of 20 AU, we still get that, right? The scale is slightly different, but the spiral is less compressed. We still have dust forming in the wake of the companion as it moves around. The image I showed at the start with W Coulé, where the companion is currently 200 AU away. Unfortunately, my student didn't send me that video in time, but we do still get a little bit of dust formation at that distance at about 200 AU, which is, frankly surprising. Probably not significantly contributing to the overall dust budget, but it wasn't zero. So basically, what you found on the AGB where there are binaries, we have two modes of dust formation. We've got the stellar pulsations we all know and love, right? The pulsations lift up gas, cools it, dust forms, dust-driven wind pushes it out. And then we have companion-enhanced dust formation. So this can have a few different effects. If the companion is far, like not close to the AGB star, maybe this just adds a little bit of dust in the second stellar envelope. Maybe it changes the dust to gas ratio a little bit. This is probably not that significant, depending. If it's very close to the star, it can still be in the region where the gas is accelerating away from the star and then falling back down. And if you look at the models of Freytag and Höfner, we still have infall within about 10 AU. So if we're adding extra dust in that area, then the dust-driven wind can pull extra gas outwards. It maybe less falls back on the AGB star, which could potentially change the mass loss rate, so increase it a little bit. So essentially, without having a common envelope or a grazing envelope, we can have binaries changing the evolution of the AGB star if they're increasing the mass loss rate. Yeah, so that's the main things I wanted to say. So the chemistry of the molecules can also help us identify these companions. And through SIN, NS, SIC, and non-carbon rich environments, which can help us find companions that are close to the AGB stars. Because if they're also making their own dust, they're shrouding themselves, which makes it even harder to see them. W Coulé, 200 AU from the AGB star, that main sequence companion is already experiencing 2 magnitudes of extinction, right? Put it a bit closer, that would go up. And that's like not even necessarily taking into account that there's extra dust forming. Yeah, so if you want to read more, I have written like a lot more details about W Coulé and about the continuum of the atomium objects, which is a larger sample than 2 stars. Thank you.
I was wondering if there were any other unusual molecules that could be indicative of UV photochemistry.
So from what we've seen so far, SIN and NS are actually probably the 2 biggest ones. Another star that I actually maybe should have included with OH 30.1 minus 0.7 has some NS, which indicates that it has a companion, and there's some weird stuff going on there. And I was listening to this morning's talks thinking I should have put that plot in, but I didn't. So they're the main ones. But in W Coulé, we also see evidence of sort of photochemistry from where the companion is now, like extra photodissociation, and then formation of CN and HC3N on the side where the companion is, because those are products of like photodissociation of HCN to get CN, and then interactions with CN make HC3N. So we sort of see that, but that's kind of, I mean, it's cool that we saw that, and that's also in the paper, but we knew the companion was there, so it's not that shocking.
Hi, thanks for a nice talk. So for the WR results, could you estimate what type of abundances you get in these nitrogen bearing molecules that you see?
So for SAN, I did estimate it. I do not remember the number right now, but it matched what Moody's chemical model said it should be for a UV induced chemistry. For SIC and NS, the signal to noise was quite low, and NS it looked like sort of like we had that arc of SIN. For NS, it looked like it was just the last bit, but it was also on the edge of a band, so it was a bit iffy. We have better NS detections in a few other stars, OH 30.1, like I mentioned before, and a few that are not published yet, coming soon.
And you think that for all of those, it's like binary.
Yeah, N2 is very hard to break up in any way that's not like photodissociation. Like you really need the UV photons for N2. It's quite hard to destroy.
I'm gonna use my role as chair here and ask you a question.
Mhm.
So the simulations are very nice. One thing I noticed with the simulation is you get, these Archimedes spirals, and you've got multiple layers of the spiral. But what you're actually seeing is only a part of an arc, right? So is that
What? Oh, yes. So the ALMA resolves out all the very large scale dust emission, plus anything that has a very low surface brightness. It's just hard to see.
so it could be there, you just.
Yeah, I mean, the resolved out flux was high. Also the scattered light sees mainly things in the plane of the sky, whereas ALMA's obviously integrating like across the whole thing. So there is some inclination there. And I think that's why we're not seeing sort of this bit in the scattered light, for example. Yeah.
One more question too, I think. So in your first system here, like what observations would you have to do to confirm your hypothesis that it's this wide, highly eccentric binary? Like how long do you have to wait before you could like determine the limits?
1,000. Yeah, no, I mean, I'm pretty confident with this one. There's no other sensible way to work it out. Like the chemistry is the strongest evidence we can get on a human lifetime. Yeah, because that star barely moved Hubble to sphere. We could like that movement agrees with our model, but yeah.
Great. Okay, let's say here again. Yeah, it's. Up next, we have Ramla Unnakrishnan, and he's going to be talking about, sorry, secret HEB envelopes for the home.
Yeah. Hey everyone, I'm Ram Lal. I'm a PhD student from Chalmers University, Sweden. So today I'm going to talk about some more ALMA stuff about AGB circumstellar envelopes. And let me begin by thanking the organizers for giving me this talk. And I should say that that picture looked so much better in my MacBook screen. Anyway, so I don't think I need to explain AGB stars to you guys. So just a quick thing, it's stars like our sun, low to intermediate mass stars. They evolve into these cool red giants known as asymptotic giant branch stars. And what we are interested here, as far as AGB stars are concerned, is the circumstellar envelope of these stars. So there is a huge envelope of gas and dust which surrounds these stars, which is very rich in chemistry and also very rich in complex structure, as we would see. So it's these are very interesting objects to study for people who who are interested in dust, who are interested in spatial structure, who are interested in molecular chemistry. So it's a lot of things. And today we will mostly be looking at some chemistry and some complex structure. So among AGB stars, what I will be mostly talking about are a subclass known as carbon-rich stars. So basically it's stars which have more carbon than oxygen in their extended atmospheres. So speaking of carbon-rich stars, the thing to note is I'm pretty sure you're all familiar with this subject shown here, CW Leo or IRC 10-16. It's one of the most studied objects in the sky, at least in the millimeter range. And so this carbon star has, as you see here, extensively observed, both for its chemistry and its complex structure. And so we we are at a stage where most of the things we know, or all the chemistry that we have constrained in such objects, we did most of it based on this star because it's very nearby and also very bright, so it's pretty easy to observe. So then one of the main goals of my PhD is to look at other similar stars and see if we see the similar things as we see in IRC 10216 in those stars as well, or if there is any difference. Because basing a lot of our understanding on a single object seems a bit, well, turns out it's fine, but yeah. So then it's very carbon rich, very close to us, has a high mass loss rate as well. So this is regarded as the archetype carbon star, if you will. And now we will see a few others. So like I said, we had this goal to observe other carbon stars. And the good thing is that now with the resolving power and sensitivity of ALMA, this is kind of easy to do. So we went down and sampled this set of stars that you can see in the table. So they also have similar high mass loss rates, which indicate that they are close to the end of their AGB phase, all of them. And they are pretty different in their 12C, 13C ratios, which in some sense indicates different histories of evolution. And so we have this sample and we have this cool ALMA data for 3 of these stars. You can see a lot of molecular lines there. So this is ALMA band 3, so around 80 to 120 gigahertz. And then we have sub-arc second resolution for most of it. And we detect around 300 emission lines. And we have pretty much all the usual molecules that you expect, like the carbon chains, because it's a carbon-rich star. And we also have silicon-bearing species. We have the cyanopolyene, so the long carbon chains. And also, like we have a potential detection of SIN in one of our stars, as Taisa was just talking about. And so we have all these cool data, a lot of molecules, but of course with ALMA, we can also see how they look like. And I can tell you already that we see typically 2 types of structures. So for the parent molecules formed very close to the star, we see a centrally peaked distribution. And for the daughter species, which are formed farther out, we of course see a shell-like distribution. And all these plots are at the systemic velocity, so in the plane of the sky. But then we also have more complicated stuff, like we see a spiral, if you will, or arcs and shells. And this is similar to what has previously been found for IRC 10216. For example, you can see the HC3N map of Agundez 2017 there. And so this, we believe, is due to interactions with a binary companion, as several people talked about here. And so there is some complex morphology as well. And with ALMA, what we do is, so these are azimuthally averaged radial profiles of several molecular species, as you can see. And we have, so we can observationally measure the emitting regions of all these species. And that comes in very handy when you want to do abundance calculations and radiative transfer and things like that. And one immediate thing to note is that, so there's a similar plot for 10216 from Marcelino there. And you can see that the order in which the chemistry happens, or for example, how far out from the star each molecule is present, which is indicative of the chemical ladder, is almost identical in all these stars. And we have the emitting regions, and early in my PhD, we did some LTE abundance calculations where things look pretty much similar to CW Leo. And then we wanted to move on to some more rigorous abundance estimates and estimating the physical properties. So we went on to do some non-LTE radiative transfer. So assuming straightforward spherically symmetric circumstellar envelope, and we started from dust modeling to constrain the dust temperature and stellar properties, and moved on to the gas and the CO. So I show you one sample SUD fit here. So we use a specific dust prescription and a circumstellar model, like I said before. And we fit the dust to get the stellar and dust temperature profile. And then we use those as inputs to model the circumstellar gas, or the CO, so as to estimate the key parameters of the gas, which are the gas mass loss rate and the gas temperature. So you can see our fits to some of the CO lines there. And with this, we then have all the initial inputs that we need to know about the circumstellar material, so that now we can move on to modeling our molecular species. So what we are doing now is we modeled CS, SIO, and SIS in these species. And so you can see the abundance profiles of CS for the 5 stars there, and our line fits look pretty reasonable, I would say. And one good thing that the one good thing that we can do, because we have a lot of single dish data as well for these sources along with our ALMA data, is that we can use both of them to constrain the abundances in a much better way than what would be possible with only single dish data. So now that we have spatially resolved information, as you can see here, the chi-square maps, if you only had single dish information, it would look like the blue lines, which is the typical banana-like thing that you see a lot in chi-square maps. But with ALMA, you can see it becomes so much better constrained that the 1 sigma and 2 sigma, for example, they're close within our grid space. But then that's the good part. But then it also comes with some problems. In that, for example, you can see here, this is for one of our stars, this is SIO line profiles. And you can see that the spatial information from the ALMA, which is from the top up to here, that's the same line, but from different beams. It fit very well, but then you see the higher J lines, which are single dish apex observations, they are not fit with the same model. But then if we go to a model where those single dish lines are much better fit, you no longer get the sum of the ALMA apertures to fit. So in the literature, what was often done is that, for example, if you get something like this, what you could do, so I should say in the beginning that we use Gaussian abundance profiles to model all this. And then if you underestimate your high J lines, for example, you could just increase your abundance for a small radius in the center where these lines would be excited closer to the star. And then that would, in a sense, solve your problem. But now that we have spatially resolved information which traces different spatial scales, we see that that is no longer a solution. So we need, but this is not something we can solve with these models. At least we need to go beyond them. And some other typical things that we do now that we have radiative transfer models is that we try to get isotopic ratios. So we have good estimates of the 12C 13C ratio, which are similar to the ones estimated from CO. And we also have sulfur ratio here from CS. And from the SIO, we could also get 28 to 29, 29 to 30 silicon ratios. And I should say these two ratios, they look almost identical to the solar abundance ratio. So this, in some sense, indicates that these isotope logs, their abundance doesn't change in the nucleosynthesis happening in the AGB phase or previously. So they are very close to their main sequence ratios. And also we looked into some issues like how important is the infrared pumping, for example, so radiative excitation versus collisional excitation. And you can see what you see at the top is the ratio of excitation temperature to kinetic temperature for our best fit models for the 3 different molecules. And you can see that when we have the infrared pumping turned on, which is the solid lines, there is significant suprathermal excitation happening there. And also I don't know if I show it here. Yes. So this is the same model, so same abundance profile, same inputs with and without infrared pumping turned on. And this is the same for all the 3 molecules in our case, that the line intensity goes significantly down. So the takeaway is that if you don't use higher vibrational levels in your molecular data when modeling species like this, you would significantly overestimate the abundance and the extent of the molecule in the CSE. So, and then we also wanted to test things like photodissociation rates, for example. So this is what you see in the blue with the error bar or the error region is our models for CS from the radiative transfer. And then the green and red are chemical models using 2 different photodissociation rates of CS from the literature. So we wanted to test which one of them matches with our derived abundance profile more, but it turns out within our uncertainties, we cannot really differentiate between them, but it's also a good test to do. So that's pretty much the different things that we do with our carbon stars. And I also wanted to quickly pivot to something else, maybe to do justice to the name of the conference and also show you something asymmetric. So, and completely coincidentally, this also happens to be the data from the next speaker. So it's a good pivot to the next talk as well, I guess. So this is another carbon star, C86. It's in Leo Minor, and it's from the literature. It's supposed to be on a transition towards becoming a protoplanetary nebula. Yeah, and what you see here is interferometric observations of the CO221 with the SMA in blue, and the red is the HC3N 4-3 observed with the VLA. And one thing you can immediately see in contrast to all the similar maps that I was showing you of my stars is that there is clear asymmetry here, that you are missing a lot of emission here, particularly in the HC3N. So it looks like there is a wedge to the west side where you don't get any HC3N emission, but the CO still traces it, but has this huge gap in between the spiral arms. And then Kim et al. In 2015, based on some hydrodynamical modeling as well, said that this is due to anisotropic mass loss due to a very eccentric binary, and also things like having a kind of a double spiral shape in the center. This also indicates this. And then we have also the same data in 13CO now. This is also Kim's data, but reduced by us. So now with ALMA 13CO, you can see the spiral in 13CO as well, whereas with the SMA we couldn't. And you can see the interarm gap as well to the west side. And what is new now is that we have this other set of ALMA observations now for different molecular species. And now you see the HC3N 11 to 10 here. And you can see that unlike the SMA 4-3, where you completely miss the HC3N in the center and the west, now you can see that it still traces the spiral arms. So that is one difference. But this data set was not limited to HC3N. We have a lot of molecular species. So HCN, HNC, C2H, HC5, and C3N. And it's good to see that you see the same dimming or suppression towards the west in all these molecules. So to me, that in some sense indicates that it's not entirely a chemical effect, but has to do something with varying densities. But there is many other complications with this stars and this data sets itself, but I don't think there is time to discuss. But key takeaway, so if you are interested in or if you have ideas about how to proceed with modeling this or thoughts about what's happening here, please come talk to me or Mark here. So I would leave you with a summary of the original thing that I was talking about. So my carbon star survey. Thank you.
Thanks for the very nice data which you showed here in your stuff. So, what is a simple explanation of the ratio which you said the single dish fluxes of the lines are underestimated? Would it simply be flux losses in the interferometric data?
Well, I mean, if we saw that only in, let's say, one of our stars, sure. But the thing is, for example, in our observations of CW Leo, we observe it with the ALMA 12 meter and the 7 meter and also the total power. And we also have other lines where we even combine with a mosaic with the IRAM 30 meters. It's basically Lewis's data. So there are cases where we are very confident that there is no flux loss, even in the interferometric data. But even in those cases, we still see it to some extent. So it has to do with using the abundance profile is clearly not well approximated by a Gaussian.
You have a quick sense of, we're seeing all these binary traces in ALMA data for, these AGB stars, indication.
You mean where we don't see any substructure like this?
Yes, where you say there's no bipolarity, there's no spirals, there's no bits and bobs.
Yeah, but I don't think it's quite that simple, because the structure that you see here, I wouldn't say it's produced by some chemistry in the wake of a companion or something. I mean, it could contribute to that, but what I feel is more like it's due to variations in the circumstellar density. So most of the structure you see is in some sense an excitation. issue. So you would see it in pretty much everything, I guess. So, for example, we have some molecules like HCN, where if we remove the very bright central component and trace the low level extended emission, we still see the arcs exactly as they are. So because it's a density variation leading to then differences in excitation in the shells and the intershell regions, I would say this is not a matter of chemical traces. So I think it would show up in pretty much everything.
Could it be that the difference between your model and the observations is because you're assuming shell or a uniform distribution
Yeah,
instead of a spiral?
Yes, that is a clear limitation of the modeling. Yes, so we
I think
assume
there's this group from Belgium doing this. They do the SPH of simulations and then gravity transfer, and they see that the actual lines are different depending on the transitions of the molecules.
Yeah, but that kind of a model, I mean, that is the natural next step to do, but I don't think it's very trivial, because if you include, like, let's say, a circumstellar density profile, which would take into account that there is this variations in the density, but then you would also have to do, like, for example, trace the temperature profile also independently, because that would also change with the density. So then it's a whole other thing, but that is the next thing to do. Yes, clearly.
This is just a comment. You have already estimated the carbon-13 ratio to carbon-12 ratio. Let's say you have already estimated also deuterium ratio to hydrogen ratio. It could be possible to estimate the deuterated carbon-bearing molecules such as cyanides, acids, metals, or you could calculate, you could also estimate the ratio of these molecules. So how in 2021, Miller published an astrochemistry article that you can calibrate the ratios by using the deuterium ratio. This would mean that you could have more material to map.
Yeah, but I don't know how strong any deuterated species even. I don't think we even detect any.
No way you can have.
No.
That's why I assume.
All right, let's thank our speaker again.
Thank you.
All right, our last speaker of the session is Sung Kim, and she's going to be talking more about spiral.
Actually not spiral. Hello everyone. I'm Hyosung Kim from Kasi, Korea. Usually I talk about spiral, but this time I will not talk about that, but about the central system, central part. I'm showing the image of IRC Canton 6 again. Actually, it's moving. It's animation showing the Hubble image from 2001, 2011, and 2016, showing the searchlight beams don't move the position angle. Anyway, I'm quite addicted to this carbon star, WLEO for now. Thanks to the organizers. I want to thank the organizers giving me the chance to share my recent works. Okay. So I'm going to talk about the central part. So the motivation is always to better understand the
shape transition from AGB to planetary nebula, and especially the asymmetry, probably launching at the end of AGB phase or at the very early stage of preplanetary nebula. And the asymmetry seems to relate to the binaries. Satisfying these two conditions, CW Leo is a target worth monitoring. Okay, so CW Leo is the closest carbon-rich AGB star, and the mass loss rate is high, forming very thick environment for the central star. And therefore, the central star was not detected in the optical images. There are 4 HST images so far. This is really very central reason of the HST image field of view. So the first 2 images showing the central part of this target around 2000. They didn't show the point source at the predicted stellar position, and they seem to show the consistent nascent bipolar nebula at the central region of this. But 10 years later, in 2011, the bipolar nebula is completely gone. It's disappeared and having some clumpy structure at the central region. And 5 years later, in 2016, the HST image shows somewhat different, a little bit different clumpy distribution. But again, the bipolar nebula is confirmed not being there anymore. In 2016, another image taken in at 0.8 micron shows the point source exactly at the predicted stellar position. And this is the reddish part in this field of view, and that red region seem to consist with the disk suggested by the polarization observation some time ago. We consider this is the appearance of the long-awaited central carbon star. This is reasonable because the star is getting brighter. As you can see, recently the stellar light curve has not only the position but has the linear brightening trend in all of JHKLM, including optical wavelengths. So this can be precursory signal for the phase transition. We have in 2016 we obtained not only HST optical images but also Gemini near infrared IFU spectral imaging data cube, which is the topic today. So we obtained this with NIPS equipped on Gemini North telescope. The spectral resolution is moderate, and field of view is 3 by 3 a second. To have better seeing, we use the adaptive optics using the super seeing mode, and these are the integrated image for JHK bands. You can see the H and K bands have a single peak, but J band has 2 peaks at the center and in the southwestern part. And these 2 peaks in J band along the wavelengths, the relative brightness changes the order. So so comparing this HST 0.6 and 0.8 micron images, the Gemini take on this data showing this, and the stellar position increases the relative brightness along the wavelengths. On the other hand, the optically brightest part reduces the relative brightness along the wavelengths. So you can see in the bottom part, you can see the SED for the stereo position has the red color, which is steeper than the other SEDs in the field of view. So using the spectral information at each pixel, we found several broad absorption features, including this this 1.53 micron feature, which is strong and very broad. That is related to the HCN and C2H2 molecules. The spectroscopic index is defined as the depth of the absorption feature in magnitude scale after normalized by the continuum, which is the fit in the orange here. The fit, polynomial fit within the entire wavelength coverage. Anyway, so there is also a very interesting feature here in K-band, which is CO Overton bands, and the first band had the spectral index of that is also calculated here. So the spectroscopic index for 1.53 micron and also the CO first bandhead of CW Leo is plotted here compared to the carbon star templates based on the X-shooter data. Boni split the carbon stars into two groups depending on this 1.53 micron feature, and CW Leo is in the group of strong feature of what this feature. And actually the strength of this feature of CW Leo is way much higher than the other carbon stars, which means the formation of these relevant molecules are active because it has very thick circumstellar envelope. And also CO spectroscopic index is low, but compared to the trend of this, it seems to be higher than the other carbon stars. By calculating this index at each pixel, we have the index map here and found the relative lack of absorption feature to the northeast here and here, which means the molecule does not exist there, which means maybe it's cavity cone here. Another interesting feature here is the lack of the ring here at 0.2 arcsecond. This is the dust forms in this system. So the dust forms at that radius and is exposed to the stellar radiation directly. So the continuum, increase of the continuum due to this dust thermal emission hide the absorption feature, so that we confirm the radius of the dust is the reason. So we have this asymmetric structure in the spectroscopic index map, but why we don't see that in this integrated map? Probably that's because the spherical halo structure is too bright. So by removing this 1/r scale spherical distribution, we can also see the faint distribution of brightness, also show lack of brightness in the same direction. This asymmetry is stronger in J-band, but weaker toward the wavelengths. So this is related to the scattered light emission, scattered light related to the geometry, overall geometry of the cone. And using the forest of lines here by cross correlation technique, we calculate the expansion velocity also, and the result is like this. And this is velocity with the lower velocity in the northern part. This result is actually consistent with the expansion velocity of the pattern in the outer part. Using the HST image in 2011 and 2016 with 5-year difference, we can measure the shell expansion. And that expansion velocity has the same result. So the velocity in the northern part is smaller than the other part, which is consistent with the current result. So this actually well, inspiring by this velocity distribution. Well, I have another story here, but I'm not going to talk about that because I already talked about that in Krakow meeting. But anyway, so using this, I make a story about the triple system, make a model, and that is quite consistent with the observation of CO shell structures. So to sum up for today, CW is still interesting target as the central star is getting brighter, and asymmetry is indicated in the near-infrared distribution on Gemini LIPS observation, providing potential hints for a biconical cavity. Yeah, thank you.
Thank you very much. Would you care to mention the orientation of the spider web plane relative to the sky?
Hi.
The orientation, the angle. I see you have a model, so you must have estimate, right?
Well, yeah, for the spider, well, the multi-layered shell structure, I haven't done the modeling. I think some other people have done. Yeah, but I actually wanted to mention this. Well, this absorption feature seems to be like a biconical cavity, and this part, northern part, is toward
I
us.
see you have a model there, so you must have an estimate for the angle.
You mean this?
No.
Well, these are like general models, so it's not particularly for
I
this.
assume you have an orbital plane, and what is the angle of the orbital plane related to the sky?
Yeah, okay. So this is the general view for this target, and the thing is actually from the HST image having like a head bipolar structure. From that image, actually we have the image and the view of this action for this target, and the the shell is another story. So originally, yeah, has, well, this shell can be like a part of spiral shell structure in the view of axiom. So that was the story. And this actually implies somewhat face on near face on eccentric binary system. That's how I was making this story. So if we have axion cross binary, cross companion, and for the outer part, the outer boundary is face on, then we can avoid this contradiction. So that's how I make this triple system story.
If I may make a comment, nice talk, by the way, it's very interesting results. But I would be a bit cautious with interpreting the brightening as an end of the HB and a start of the post-HB, because carbon stars do this. They show variable extinction, various dust formation, then they fade a while for a decade and they brighten again. So as far as I can see, this is normal behavior for carbon stars. Tricia Whitelock has published several line curves of carbon stars like RLAB that show this kind of behavior.
Okay, thanks.
Any other questions?
But slightly related to what Albert said, the brightening could also indicate that there might be a thermal pulse, or it could be a long secondary period, which would fit with the binary. There's some more options. Thanks.
All right, let's go ahead and thank our speakers. Okay, and now we have several posters. We're going to start the posters now. Just remind everyone that after the session, we can go out through the posters and ask questions there. First up is Genji 10.
Okay, thanks so much. Hello everyone, or I should say hola a todos. So I'm Zhen Jie Tian, a PhD student in the Laboratory for Space Research of the University of Hong Kong under the supervision of Professor Quentin Parker. And today it's my pleasure to present my research with Professor Parker and Dr. Sajadi in such a wonderful conference. Our title, The Rise and Fall of QB1, which is a follow-up work to the exciting discovery of the inside-out planetary nebulae by Dr. Martin Guerrero here and Dr. Xuan Fang, which is out here. And their work has been published as a cover letter of the Nature Astronomy in 2018. So it's very exciting. And in this study, we present the most comprehensive light curve data of QB1 in B band. And by combining the light curve data from the DASH by newly published DASH data from Harvard College Observatory with the photometric and spectroscopic data from other surveys. And it's the very first time that a brightening process has been discovered on QB1 and then suddenly dimming. And we believe, and through which we construct its evolutionary tracks. And also we believe this sudden dimming is caused by the dust formation. Hence, we estimate the timing of the dust formation and obscuration is around 1983. And moreover, we estimate the dust mass
based on the extinction from its light curve and also from the black body fitting to its SED. And it's interesting that we found the dust mass as estimate from the extinction agrees well with the cold dust component based on the SED fitting. And yeah, if you want to know more about QB1 and the dash, we can discuss later through a coffee break. And finally, I would like to thank Professor Parker for planning and helping for the whole project, and Dr. Sajadi for the help on the dust analyze, and also Martin for providing the valuable data from his previous study, and also Albert for a valuable suggestion. That's why we have this note. Okay, that's all. Thank you.
All right, next up is Roberto Vasquez.
Thank you very much. I'm very happy to be here in Granada because it was my adoptive homeland when I started my PhD some years ago. So I'm very happy to be here. This work is about the very complex planetary nebula NGC 2371. It's about the morphokinematic structure. This subject has a kind of axisymmetric morphology, but it is not that classical bipolar nebula with a very defined waves and lobes. It's more strange. Some of you have been studies about this in the past, and even more recently. We know that it has a white dwarf hydrogen deficient star, and also we know something about the chemical abundances, etc. This work is only focused on the morphokinematical structures. We observe with the Manchester HL spectrograph and the 2-meter telescope in San Pedro Martir, Mexico, and we obtain these position velocity diagrams and different position angles and even in different locations. With this data and with images, we try to make a model with the ShapeX software from Wolfgang Stefan and Nico Koning. And we propose some structures that can reproduce by very well from our point of view, very well the position velocity diagrams and the images at the same time. So we find some structures like a barrel-like in the center with separated caps, and also this little bit deformed bipolar structure here. No? And you can discuss this about in the after that, the model, the object, everything we do well. No? Thank you.
And next up is Mark again.
Can't get rid of me, sorry. And I have good news because I'm going to go from talking about a weird object that's hard to explain to talking about a really, really weird object that's really, really hard to explain. So I mentioned before that I actually spend most of my time looking at massive stars and red supergiant mass loss. And this is an important thing to do because red supergiant mass loss is not very well understood. And it's very important to the appearance of type 2 supernova. And we have very few constraints on actually how this mass loss occurs or how it varies with luminosity. So what we did was surveyed a cluster of supergiants near the galactic center called RSGC2, just to look at their CO emission with ALMA to get some very basic mass loss rates and have a better sample size for the RSG population. And we were surprised with one object called DFK52, which to date was just kind of a normal member of the cluster, but we find this gigantic CO envelope surrounding it And if we use the cluster distance, which is the best distance we have right now, it's about 90,000, 100,000 AU across, which is 3 to 4 times bigger than VY Canis Majoris. And it does that while at the same time having a luminosity that's a factor of 10 lower than VY Canis Majoris. And you should hear those numbers and say, that's impossible. And we agree, we don't know what's going on with this source, but we know that it has some kind of really dense detached ejection. And we actually see kind of an equatorial enhancement that we're viewing somewhat edge on here with this bar component. And this detached nature is also reproduced in the SED, which is may or may not be visible here, but it's a 2-component SED with a very cold component as well. So we think this thing lost about a solar mass of material all in one go about 4,000 years ago. And we're still trying to figure out exactly what it is, but happy to talk more about it.
Mario, put a round of applause for all of today's speakers, and we can continue this great science discussion at the conference.
I use this one actually, looking at the history of things, I've seen this before, of course, I used it in China.